Welcome, everyone. Welcome back. We are moving on to our next part of our motion notes, which is free fall. And this is going to be pretty exciting. We got a cool lab we're going to be doing soon, and some cool graphs. We're going to kind of introduce gravity. So instead of thinking about motion of objects moving this way, we're now looking at motion of objects going vertical, so things falling. So the definition of free fall is an object under only the force of gravity. So no air resistance, nothing's touching it. So typically, air resistance messes up calculations because air resistance is different for every object. The air resistance of a ball is different than the air resistance of a piece of paper. So even if they have the same mass and the same size, their air resistance is going to be different. So in order to simplify things, we look at no air resistance, nothing touching it. So we're going to make that assumption for most of our problems. So with free fall, object under only the force of gravity. So even if I throw something up and there's gravity, but no air resistance, nothing's touching it, no air, no nothing. If I throw it up, it's still in free fall because only gravity is affecting it. And then it's eventually going to fall down. So the whole pathway, you would say it is under free fall, going up and down. So don't be misled by the word fall. As soon as you throw it up, it's in the process of falling. It just isn't going down yet. It has to go up first before it goes down. But it's still free falling. Still free falling. Still falling. It's just kind of not downward falling yet. It has to do the upward part first. Hope that makes a little bit of sense. So an object's motion in free fall is independent of its mass. So the mass does not make a difference in free fall. So what that means is in free fall, a 100-pound rock and a feather would both hit the ground at the same time if they drop from the same height at the same distance. So if we have a feather and a rock and we drop them, they would hit the ground at the same time. And we're going to look at a demo in class, and we're going to watch some videos in class that demonstrate this. It's kind of counterintuitive because we don't really experience it in our everyday lives. So on Earth, gravity accelerates all things at 9.81 meters per second squared. And it accelerates them down at this rate. And we're going to round this to 10 when we do our calculations. So whenever we're doing math, we're just going to round it just to make the math a little bit easier, but no, the actual value is 9.81. So let's take a look at an example. Let's say we start at time equals 0, nothing's moving, everything's 0. After 1 second, gravity is accelerating it down -10. So if we drop it, it's now moving at -10, and gravity accelerated it down at -10. In 2 seconds, it's now going 20. Or -20 because it's going down. In 3, it's going -30. After 4 seconds, it's -40, and on and on and on, because you can see the acceleration on Earth is -10 meters per second squared. So the change in velocity is going to change by -10 every second. All right. Next slide. Oops, there we go. But of course, on Earth, we have air resistance. And so air resistance is a frictional force, and we're going to talk more about frictional forces in our next unit. But I do want to kind of introduce it here. It's caused by air, it slows down objects, and it's affected by many things: size, shape, texture of an object. So because of this, it's hard to calculate. It's beyond the scope of this course. We're not going to talk about how to calculate air resistance. We're just going to mostly assume it doesn't exist for most of our calculations. Terminal velocity is the fastest speed an object can fall caused by air resistance. So if you drop something, like a piece of paper or a feather, it doesn't keep accelerating. It hits a terminal velocity and it stops speeding up, and it just kind of floats at that same speed as it falls the rest of the way down. So most things will hit a terminal velocity as they're falling. And once again, it depends on all those things. So here's an example of falling with air resistance. If I tell you, which I may on a test or a quiz, that something has a terminal velocity of 20, terminal velocity is the highest velocity an object can fall. So what it would look like is it starts to look like normal. Gravity is accelerating it at 10. Negative 10, because it's going down. And then after it hits the terminal velocity, so the terminal velocity is negative 20, it's going to continue to stay at negative 20. So since A is 0, because once it hits terminal velocity, it's not accelerating anymore, which means that there are two forces. Gravity is pushing down and air resistance is pushing up, and they're basically canceling each other and wiping each other out. So what you need to know about this, if I give you a terminal velocity, an object cannot accelerate past that point when it's falling, because the force of gravity is going to be canceling the air resistance. So the down and the up are canceling, and if there's nothing pushing on it, it's just going to keep going at the same speed. All right, let's talk about throwing up. And I'm not talking about this throwing up, I'm talking about throwing an object up in the air instead of down. So if gravity always accelerates down at negative 10, when something is going up, it's decreasing by 10. So the velocity is decreasing by 10 as it goes up. At the top, the velocity is 0. There is still an acceleration, though. The acceleration is negative 10. And I think it'll make more sense on the next slide. So gravity's still pushing down. It's now 0 at the top. And now it's going to start speeding up as it goes down. On the way down, objects speed up, but they're still speeding up at negative 10 because they're speeding up going down. So it's still negative 10. So a picture's worth 1,000 words. So let's take a quick look at this picture. If Meeps here in the dress throws a baseball up at 30 meters per second, after 1 second, the ball will be going 20 because it accelerated at negative 10. So remember, acceleration is the change in velocity. So the change was negative 10 in that first second. During the second second, the velocity is now 10 because the acceleration of gravity is negative 10. It slowed down by 10. In the third second, it's going 0. What was the change in velocity? The change in velocity was negative 10. So it's at 0. The acceleration is not 0. If there was no change of velocity, if the acceleration was 0 up here, then that would mean the velocity is not changing. That means it would stay 0, and it would just be hovering in midair. That's impossible. The fourth second, it's going to start coming down. It's being accelerated. It starts here. It's being accelerated down at negative 10. So now it goes negative 10. In the next second, it's now going from negative 10 to negative 20 because it's changing down by negative 10, and then negative 10 again. So the acceleration is always down negative 10. So it's decreasing the velocity on the way up because it's against the acceleration, and then it's increasing the velocity on the way down because it's going in the same direction. The object's going down and gravity's pushing it down. I had a fly buzzing my head. You'll also notice that the velocities are mirrored. So at this point at the bottom, it's 30 meters per second. And going up and coming down, it's negative 30 meters per second, but it's 30 and 30. At this point, it's 20 and negative 20. At this point, it's 10. It's a mirror image going up and down. It's at the same velocity. Okay, actually, I take it back. It's not the same velocity. It has the same magnitude of the velocity, but the direction's different. So the velocities are actually kind of opposite. Same size, different direction. All right, Moops throws a ball upward at a velocity of 60. How fast is the ball going at the top? I just gave you the answer 0. Let's do another one. What is the acceleration at the top? I just said it on the previous slide. Can you get the answer? Hopefully you said negative 10. How fast is the ball going right before it hits the ground? Did you say negative 60? I hope so. How long is the ball in the air? I didn't talk about this directly, but how long would the ball be in the air? The ball's going to be in the air for 12 seconds. It's going to take 6 seconds to go up because it's going to go starting at 60. It's going to go 50, 40, 30, 20, 10, 0. That's 6 seconds. And then it's going to come down 10, 20, 30, 40, 50, 60. So that's 12 seconds. Hopefully you got that. If you didn't, don't worry about it. We're going to talk about it in class, and we're going to dive into some math in class. Looking forward to seeing you guys. See you soon.